We're going to talk about the next section of 7.4, which is integrating by trig substitutions. This is very similar to when we did a u substitution, where the goal is we want to replace something in the integral with something else equivalent that's easier to integrate, and then we'll replace back. This works for expressions in the integrand that have the form of a squared plus x squared, or radical square root of a squared plus x squared, or radical a squared minus x squared. Let's consider some trig relationships first, and then we'll jump in and look at some of the integrals. So if you look at the triangle on the left over here, we notice if I had some expression x and a, if I think of those as sides of a triangle, if I write this way, then notice that the sine of theta would be x over a, and this missing side here by the Pythagorean theorem is going to be the square root of a squared minus x squared. And the triangle on the right, it would be that the tangent of theta equals x over a, and this missing side here, the hypotenuse, would be the square root of a squared plus x squared. Notice that a squared plus x squared and a squared minus x squared is what we're looking for in the radicand. Let's look at an integration example to see how this actually helps us now with the integrals. So let's consider the following example. I want to integrate x squared over 16 plus x squared dx. As you get going, you'll be able to notice some patterns for these trig substitutions and not necessarily have to draw the triangle. That's fine as long as you're consistently getting the right answer. I find the triangle helpful. First, a couple observations. This is a quotient. I might consider partial fractions, but I notice that the bottom is already an unfactorable quadratic, so I'm going to end up going in circles there. If I think about doing a regular u substitution, I get stuck because neither of these functions are derivatives of the other. Similarly, if you were to start trying to do integration by parts, this is going to be quite the nightmare. Of course, this is sometimes, like we've talked about before, some of these are on the tables. If you can already find the formula on the table, that's always an option, but this is a way you can do it by hand as well. So I notice I have 16 plus x squared. I'm not going to call that u, but what I can look at is that if I consider some other variable theta, and I call the opposite side x and the adjacent side 4, then the tangent of theta is x over 4, or x is 4 times the tangent of theta. So instead of calling x u or x squared u or 16 squared plus xu, what I'm going to use is this substitution right here, that x is 4 tangent theta. At first thought, I know some of you are thinking, why would I do that? It doesn't trig stuff usually make my life more challenging? And the answer is no, because of this triangle relationship, where I realize, by the way, this hypotenuse would be written as the square root of 16 plus x squared, is going to make it a lot easier. So let's go ahead and do the substitution. Once you set up the substitution, it's exactly the same as a u substitution. I am now trying to replace everything in the integrand in terms of theta, with the goal being I get something easier to integrate. So the same steps. First I take the derivative. So in this case, dx is going to be 4 over the cosine squared of theta. If you like to use secant squared of theta, that's fine. D theta. And now I can start substituting, right? So if I look at it over here, whoops, let's get back to the original integrand. My x is going to become, replaced x squared will become 4 squared tangent squared of theta in the denominator as well. And then my dx is going to be the 4 over cosine squared of theta, right? And all of the x squareds, I'm going to replace using the relationship that x is 4 tangent of theta. Let's try that and see what happens. Whoops. Let's skip to a new page here, right? So we had originally x squared over, I want the integral of x squared over 16 plus x squared dx. We said that 4 tangent theta is x, so that dx is 4 over the cosine squared of theta d theta. So now substituting, x squared becomes 16 tangent squared of theta. Here my 16 is still 16 plus x squared, which is 16 tangent squared of theta. And the dx is going to be times 4 over the cosine squared of theta, all times d theta. Right? So again, x was 4 tangent theta. So I use that to substitute for the x squared. And dx is 4 cosine squared of theta d theta. What you need now is to remember a trig identity that says 1 plus the tangent squared is secant squared. Oops, that is not what I wanted to do. 1 plus the tangent squared is the secant squared. So we'll put that here. 1 plus tangent squared of theta is the same as the secant squared of theta, which of course is 1 over the cosine squared. So if I factor out a 16 and simplify things, I'm going to get something a lot easier to work with. I recommend that you pause now and see what you can simplify on your own. So hopefully, and I will practice trying to learn how to use the scroll down button here. Hopefully once you do all that, you factor out the 16. So then that reduces. You can pull the other 4 out. You'll notice that when you substitute the, we're going to still have the tangent squared of theta on the top. And then my 1 plus tangent squared of theta on the bottom becomes secant squared of theta. And I still have 1 times the cosine squared of theta, d theta. Secant squared and cosine squared are reciprocal. So secant squared times cosine squared is just going to be 1. So now, whoops. My computer is not being happy with me. So now, oh, okay, it doesn't want me to work on y plus there. So now if we can come back to what we were doing. So now what we're left with is 4 tangent squared of theta d theta, which is in fact something we can integrate more easily than the original expression we had. Here you could either look it up on the table or you can continue to use trig identities. Right? Tangent squared is, of course, sine squared over cosine squared. And then what I would do here is replace sine squared with 1 minus cosine squared. And now I can break this up into 2 different integrals, right? Everything's still times 4. So this is going to be the integral of 1 over, oops, I forgot my theta. Cosine squared of theta d theta minus the integral of d theta. And from there, it should be pretty clear. We have 4. The antiderivative of 1 over cosine squared is, of course, tangent of theta. And the integral of d theta is theta. And then we have